Howdy and welcome back. So transferring ownership explicitly with the standard library move function. So I don't know, a disclaimer before we get going. The standard library move function does nothing but cast its arguments to an R value. It doesn't move anything. It simply performs a cast. Scott Myers in his text, Effective Modern C++, says that this really should have been named something like standard library R value cast because that's what it's actually doing. It's simply going to take its argument and it will give you back that argument cast to an R value. So the standard library move will allow us to invoke our move constructors and move assignment operators explicitly. Why? Because remember, those operators, the type of their parameter was an R value of the object of the same type. Now we have a way to get an R value of the same type. And that's going to be done using move. So I'm going to go ahead and set this up real quick. I'll pause and then I'll come back. I'm going to draw out a nice, wonderful diagram, and then we'll revisit the second part of this together. Okay, so just drawing this out, what does V1 look like? So we're using our parameterized constructor here to construct a standard template library vector housing integer objects identified by V1. This object will be placed on the stack, and if you remember, it has kind of multiple fields, and we're only going to concern ourselves with size and then the field that is storing the pointer to the dynamically allocated array owned by V1. So I named this v1.array underscore, and then the size field v1.size underscore. The actual namings of these fields for a standard template library vector could vary, but the idea that we're showing here is nonetheless the same. So here's v1. Now let's go ahead and consider this statement. Standard template library vector of ints v2 is going to be initialized with v1, but as an R value. So this line here is going to give us back a standard library vector of int ampersand ampersand or R value type. So that's what V1 is cast to here. And now look, we have initialization, but the argument on the right-hand side is an R value. So we can go ahead and assume that standard template library vector has some sort of default constructor that is going to take an object of the same type as an R value. And that is the case. This is defined. So standard template library vector does have a move constructor defined for it. And that is what's being invoked here to construct V2. So here's what happens. V2 gets pushed to the stack. Let me do this in a different color. V2 is pushed to the stack. It's going to have, again, I'm only considering two fields here. A field storing the pointer to the dynamically allocated array, and then a size field, just to make this easy. Now, what's going to happen for this move operation is first going to be a memorized copy. So what that's going to mean is V2's array is initialized with the address stored in V1's, which means those two objects are pointing to the same dynamically allocated array. Likewise, V2's size is going to be initialized with whatever's in V1's size. That's the integer value of 3 because V1 is a vector storing 3 elements. Okay, now here's where we begin diverging from the member-wise copy. We're going to go ahead, since V1's resources have been, in this case, kind of stolen by V2, we're going to go ahead and set, hold on, V2 or V1's array to point to the null pointer to break that connection. So directly before this, after the member-wise copy, we had two objects, V1 and V2, sharing the same dynamic resource. Our move constructor, after getting to that point, will then begin to diverge these two objects. So V1's array will point to nothing because it no longer owns the resource. V2 does. And at this point right here, this ownership transfer of that dynamically allocated object has been complete. You can see here, V2 is pointing to the dynamically allocated array that V1 once owned, and V1 is pointing to, well, its array, the null pointer, because it has no elements anymore. Its array was taken by V2. And then what we're going to go ahead and do is just zero out or update the relevant data members of V1 to reflect this change in kind of resource ownership, which means it no longer owns 3 elements. It owns 1. And any other data members that would need to be updated to reflect the change of ownership of this resource, those changes would be made after the resource transfer has been completed in our definition of the move constructor. Or if this was an assignment statement, we'd make the same, we'd go ahead and make the same changes in our move assignment operator's definition. And that's what we're going to go ahead and look at here. So let me draw this real quick to set it up, and then we'll walk through it together. Okay, in this case, because we're looking at move assignment, we're dealing with 2 existing standard template library vectors. So each is going to own its own dynamically allocated resource. Now we're going to go ahead and assign to V2 V1. However, the argument presenting on the right-hand side of our assignment operator is going to be an R value, because standard template library move is going to cast its argument V1 to an R value of its type. So in this case, we have a std vector of int R value presenting on the right-hand side. This will prompt our move assignment operator to be invoked. Now, the first thing we need to do here is, because we're dealing with assignment, meaning the object on the left-hand side has already been built up and potentially owns some resources, we'll first check for self-assignment as we did in our copy assignment operator. And then thereafter, we're going to go ahead and free the resource on the left-hand side. So V2's array is going to have delete invoked on it because we no longer need it. We're just like in copy assignment operator, V2 for move assignment operator is getting new data. So we go ahead and release its old data, but again, only after checking for self-assignment do we go ahead and free its old data. And then what we're going to do is go ahead and begin that shallow copy of V1. So we'll go ahead and take V2's array and assign it the address stored in V1's. So at this point, we have that shared resource scenario, and we'll go ahead and update V2's size to be that of V1's size. In this case, it's the same as before, but we're going to go ahead and make that assignment anyways. Okay, now we're at the point of diverging, right? V2 has successfully stealed V1's dynamically allocated array, and we perform that member-wise copy. So it's going to be identical in its internal state for the most part to that of V1. So now we need to begin unhooking V1 so that the ownership transfer completes, because right now they're both holding on to it, this object, or I guess the dynamically allocated resource. And at the end, we want V2 to come out with that. So within our move assignment operator, we'll go ahead and update this pointer to point to the null pointer. So at this point, there's no more resource sharing. And the next thing to do is to reflect this change within V1's internal state. So V1 doesn't have a size of 3 anymore, it's got a size of 1. And at this point, we successfully transferred the resources associated with V1 to V2, and we've updated V1 state to reflect that it no longer owns the resource that it once did. So hopefully that kind of makes sense. So the move semantics are already defined for the standard template libraries vector. I'd like to go ahead and now define them for our doubly linked list so you can see what an actual implementation looks like.